Good afternoon, everyone, and welcome to the third session in our special seminar series commemorating the 25th anniversary of UNIGIS Portugal and the Master in Geographic Information Systems and Science. Over the past quarter century, this program has played a central role in training Portugal's geospatial professionals, advancing GI science, and shaping the way we understand and manage our world through geographic information. Today's session continues that celebration by focusing on one of the most compelling frontiers in our field, monitoring dynamics in ecosystem service indicators with remote sensing. Over the past decades, Earth observation has transformed how we understand environmental change. Satellite data allow us to observe ecosystems consistently across large spatial and temporal scales. This is particularly important for ecosystem services such as carbon storage, water regulation, biodiversity support, and agricultural productivity, which change over time in response to climate variability and human activities. Remote sensing enables us to move from static assessments to continuous monitoring of ecosystem service indicators. By combining satellite time series with spatial analysis and ecological modeling, we can detect trends, identify early signals of change, and better understand how ecosystems respond to natural human pressures. Today's seminar will highlight how these approaches are applied in practice, showing how remote sensing can support ecosystem monitoring and contribute to more informed decisions for sustainability and conservation. It is my pleasure to introduce Professor Pedro Cabral, who will deliver today's seminar. Professor Cabral is a faculty member at Nova Information Management School, Nova MS, and is widely recognized for his outstanding work in ecosystem services and the application of remote sensing to environmental monitoring. His research focuses on how Earth observation data and spatial modeling can be used to map, assess, and monitor ecosystem services and their dynamics over time. Through numerous research projects and scientific publications, he has made important contributions to advancing geospatial approaches for understanding and managing ecosystems. His work bridges remote sensing, spatial analysis, and sustainability science, supporting better environmental decision-making. Please join me in welcoming Dr. Pedro Cabral.
Okay, so thank you very much. Good morning, everyone, or good afternoon for you. I would like to thank the invitation to be here. It's a big pleasure to me. And today I'll talk about monitoring ecosystem services using remote sensing. So we now have satellites that are covering almost 90% of global ecosystem stages based on more than 40 years of Earth observation data. So in theory, we should understand ecosystems pretty well by now, right? But in reality, we mostly understand how complicated they are. So the question is not really if we have the data. We do have the data. We clearly do have the data. The real question is, what are we actually measuring? Okay. So I will walk through this presentation in 8 steps. Don't worry, I won't spend equal time on everything. Some parts are more important than others. And some slides are here just to make this presentation longer, a little bit longer. So let's start simple. So what are we actually doing when we say remote sensing? Remote sensing is acquiring information without physical contact, which is great. So basically that's what I do in my life. So I'm this guy here sitting on a chair the whole day. So I analyze data, I create models with data. That's how I'm working with monitoring ecosystem services. So But more importantly, remote sensing allows us to observe ecosystems continuously across space and time. And that really changed the way we do environmental science, right? So we don't really need to leave the office. We can control a lot of different things just by using data that is collected continuously over time. So there's been a great evolution in satellites and in remote sensing in general. So we went from very rudimentary ways of collecting data to a big constellation of satellites. And unfortunately, or fortunately, the data got very good, right? So there's been a big technical evolution. So we have better spatial resolution, we have better temporal resolution, and also spectral resolution. So basically, we can observe almost everything, right? So maybe except what we actually care about. So naturally, we are applying this to everywhere, right? So we have remote sensing covering everything on Earth. And for this, we can create multiple applications, and there is multiple applications of remote sensing that includes deforestation, urban growth, conservation, etc. So remote sensing is everywhere, okay? So you can even use remote sensing to influence policies, but there's the uncomfortable part, because better data doesn't always guarantee better decisions. So, and this becomes very clear when we move to ecosystem services. Probably I've heard about this definition. So ecosystem services are the benefits that ecosystems provide to humans. This includes food, water, climate regulation, recreation, etc. So basically, it's everything we get from nature, okay, for free. So, which is very good. So we actually, and this became very important, especially after the Millennium Ecosystem Assessment Report that was published in 2005. You can download it for free. This became a very influential idea that has been raising more and more people to work on this subject. And I can say that ecosystem service has also become part of planning and legislation. So it's becoming really much used for decision making, okay? So they come up with this categorization in four classes, which is quite elegant and intuitive. So we have basically four types of ecosystem services. They are written there. But it's also a little bit misleading because it suggests that we can measure these links more directly than we actually can. Okay, so it looks like it's simple to measure, but that's not actually the case. So, and here we have the human well-being. So they all these four categories of services, they contribute to human well-being. So this is human-centered. So ecosystem services is only when the benefit to the humans is realized. So this is completely human-centered approach. Okay. And then we did what scientists always do when they want attention. So we also provided a value. So we put a price on ecosystem services. And there is this very important paper that was published in Nature, by Costanza and several other authors in 1997, so a long time ago. So they came up with this huge number, which is either incredibly insightful or completely meaningless, depending on your mood, I think, because this is also a little bit difficult to defend. And they come up with many calculations, but of course, this is just an approximation of the values of the ecosystem services. So this is intuitive and powerful concept that is widely used. And this is exactly why we should be very careful with it. So when we take decisions, we should be aware of what's behind the calculation of these indicators and how we are measuring ecosystem services. So let's talk a little bit about monitoring, which is the topic of the talk. So we rely heavily on remote sensing to monitor ecosystem services. And this is where things get tricky or more complicated. So, but the problem is ecosystem services cannot be measured with remote sensing. So, sorry for disappointing you. Maybe we're not expecting. I was going to tell you this now. Actually, this is the title of the talk. But we cannot measure them directly. We need to use proxies, okay? Ecosystem services cannot be measured directly from space, as I mentioned. So I'm repeating this on purpose. So what we can do is observe proxies with remote sensing, proxies of ecosystem services. So what do we actually measure? So we measure things like vegetation productivity, soil moisture, land cover, etc. There are many things we can measure with remote sensing, and then we need to interpret them as ecosystem services. So this is a very important step because we all interpret things differently. It depends on our interests and on our objectives. So going from observation to interpretation is where most problems happen, okay? So this is how this works conceptually. So we have this chain. We go from drivers and processes to indicators, ecosystem service indicators. And then we try to figure out how do they benefit society, okay? But remote sensing is really at the beginning of this chain. Everything else from here on is interpretation. So we need to take this very carefully because sometimes we try to give meaning to things that are not really ecosystem services, okay? So if we start working on this, we'll quickly realize that there are many ecosystem service indicators. And I just put here just a few, but I could easily come up with a table with hundreds of indicators. There are too many. Everyone defines them differently. So consistency becomes a little bit optional in this case. So there's a lot of things going on, people trying to come up with the better indicators, but there's still a lot of work to do because depending on the way we implement the indicator, we are measuring different things, okay? And sometimes they are saying they are the same things, but they are not. So, as I mentioned, so consistency, it's really important because if you really want to monitor something, you have to come up with indicators that you can measure regularly and consistently over time, okay? So I have put here some examples of ecosystem service indicators for each of those categories. Not all of them are to be measured using remote sensing. For remote sensing, I have this bigger table here. I hope you can read it. But basically, these are examples of indicators obtained with remote sensing. So they all have advantages and disadvantages, but each one has its own assumptions, limitations, and each one measures something slightly different than what is sometimes claimed, okay? And for some of these ecosystem services, we can still also add some calculations regarding valuation. So we add money to the equation, and let's say like this, because also apparently everything becomes clear when we assign money to measure something, except it doesn't, right? So that's why we need models. we need models. We can use machine learning models. I've been using machine learning models to calculate ecosystem service indicators, or we can also use process-based models. An alternative approach is to use a balance between machine learning models and process-based models, so we can call them hybrid models in which we make some compromise. So machine learning are rather flexible models. We can use multiple algorithms, but they lack interpretation, which is more difficult. But the process-based models are more interpretable, but on the other hand, they are more difficult to implement and require more data sometimes, which is not always easy to get. So I think everyone loves machine learning until they need to explain the results, right? So, and also when working with machine learning models, we tend to use those as accuracy metrics. Sometimes we get very high levels of accuracy, but that doesn't really mean that we can obtain meaningful insight from those models. So especially when we are working in policy contexts, okay? So now let's make things a little bit more complicated, and also because we are in a UNIGIS talk, I imagine that you are all familiar with satellite data and scale, concepts like scale, and also uncertainty. And so let's talk a little bit about this. So when working with satellite-derived ecosystem service indicators, we also need to be aware that there is a scale mismatch between what we measure at pixel level and what we interpret at regional or policy scales, okay? So that mismatch creates errors that we often ignore. So we really need to understand what kind of data we are working on. Okay, so we need to be acquainted or familiar with geographical data. You need to understand what are pixels, vectors, and you need to understand what is the satellite actually measuring, okay? But then when we are going to take this into decision making, we need to do some kind of aggregation. Can be using administrative areas, can be using management areas. So we need to understand that we are generalizing those measurements. And of course, that if you do some kind of aggregation, we are smoothing the indicator. And the inverse is also true. If we are using a very detailed representation, we are exaggerating noise. Okay, so basically we are always wrong, just a little bit in different ways, right? So regarding uncertainty, we need to be aware, especially when working with geographical data. So uncertainty accumulates everywhere, okay? Since the data collection to the interpretation, which is our final step when working with ecosystem services. So I would say that the biggest uncertainty are the conceptual assumptions, trying to use indicators to measure something that is not directly measurable. So we need to be very attentive to what kind of interpretation we are making from our measurements, which do not correspond, as I mentioned before, to ecosystem services, but to indicators of ecosystem services. So here I make a workflow for a general workflow for remote sensing based ecosystem service indicators. So we start with data acquisition. So which satellites or which satellite data we are going to use. So in the first slides I showed you a big constellation of satellites. They are all different. Depends on really what you want to do. Also, if you need to pay for the data or if you want to get it for free, there is a lot of free data. But they are all different regarding spatial, temporal resolution, also they are different in the way they measure the phenomenon, and sometimes they are also different in the difficulty in processing them. Sometimes we need to use more complicated pre-processing algorithms, or we can actually use already ready-to-use products derived from those from that data. Basically, in my line of work, that's what I'm doing. I'm not classifying original satellite data. I'm already using ready-to-use products like NDVI over big temporal series of data. But we need to understand how those variables were acquired and processed, and if they fit the objectives of our study. Okay, so then we need to come up with indicator calculation. We need to understand especially if we are using already products that have been processed, we need to understand what they mean. Okay, sometimes even if they have approximate names, they have different calculation algorithms, and they represent slightly different things that we need to be aware of when working with ecosystem services. So then we need to do some kind of indicator aggregation when we're creating those beautiful maps to show planners. And then we need to come up with some interpretation for decision making, which is supposed to be easy to read and to understand so it can be implemented. So we can use tools like Invest. Invest is a tool which is developed by a team at Stanford University. It's a free open source tool you can download for free. And it has a suite of models. I don't remember how many models there are, maybe 15 or between 15 and 20. They are constantly changing it. There are also other tools like Arise or others, but I confess I only use Invest. I'm also using Python to create indicators, which are not necessarily given by Invest. So Invest is not for everything. Sometimes you need to calculate things that are not made available in Invest. So that is why it's also important to know how to work with spatial data, how to work with data science. Okay, we are using a lot of machine learning nowadays, and we really need to know how to implement data pre-processing pipelines so we can calculate those indicators and then map them and create those beautiful maps in the end. Okay, so Invest, we have here a generic workflow also. So we can use land cover maps as input data. Land cover maps are usually also obtained from remote sensing, right? We might need some biophysical parameters depending on the model we are using. We can come up also with drivers, spatial drivers like distance to roads, natural areas, precipitation, gross primary productivity, etc. And then we can calculate several types of indicators. Okay, so those indicators are created and usually special because we are interested in monitoring, right? So we want to use time series of data. Okay, so this is a challenge because you want to use multiple variables that were acquired with different scales, different dates. So we need to know very well how to process those data sets so we can come up with some variables that can be work together to create in a meaningful way and also in a correct way a strong indicator map. And also we need to think about how to validate those results. So we can create indicator maps in multiple ways, but the hardest part is to get meaningful interpretations and, if possible, also do some meaningful validations so we understand and we can defend the value of our work. Because, you know, when you throw data to models, they always come up with something in the end. And it's not always easy to defend the quality of the work you are doing. So So when you come up with some indicators, and we are working also with time series, you can also estimate future changes, okay? So if we are working with ecosystem services based on land cover, we can do estimations of land cover for the future. And then there are actually many types of data sets that we can download for free with scenarios, climate scenarios, and then we can estimate the changes in ecosystem services according to those scenarios. That's some kind of work that we have also been working recently here in China, where I'm based on. Okay. So what happens in practice? So I have put here some case studies related to some works I've been doing there at Nova AMS with students. This is a work done by Bruna. She did a very interesting paper that was published in Applied Geography. So this paper is about, it's a literature review about the ways that we can use remote sensing to estimate ecosystem service indicators. So this was for her PhD thesis. It was also part of a FCT project that we developed at Nova AMS. But she did a literature review, so she collected all the papers about remote sensing that were about estimating ecosystem services, and she answered some very interesting questions. So which are the most used satellite data, which are the most used algorithms of machine learning, which are the most used services to be calculated using remote sensing. So this is a very useful paper, and it's in a very important journal, and really shows what we can do with remote sensing for estimating ecosystem services. This is a very old work I've done in France when I was working on a postdoc, and this is a 2-year project. We also use land cover, in this case, Korean land cover. This work has more than 14 years, actually 14 years. So, and we involved stakeholders. So remember the definition of ecosystem services. We always start with stakeholders, because this is about the benefits society gets from the ecosystem services. So if you want to manage something at a territorial level, it's important to involve stakeholders in the decision-making process, so they understand the concept and they also embrace the concept so it can be applied in their management. Okay, so we consulted the stakeholders so they could decide which were the important ecosystem services. So, and then we developed the study around the stakeholders' opinions. Okay, so after the first year, we showed them the results of the first iteration, and then we fine-tune the results so we come up with a final product that fit their interests. So basically, we use Korean land cover for Bordeaux, and we show the changes in ecosystem service at commune levels, and we also showed what was happening in Bordeaux from one day to the other, what was getting worse or best or consistent or constant. Okay, so there are many other studies we have done at Nova AMS, this is a project, 2 projects from also a PhD student that recently defended her PhD at Nova AMS. She integrated ecosystem variables in machine learning models to estimate landslide susceptibility maps, so which is a very interesting approach. She also estimated habitat quality. Habitat quality is not an ecosystem services, but it's an indicator that if it's good, it shows that the conditions to produce ecosystem services there. So that's why you should keep habitat quality high. So she did this for Brazilian Upper Paraguay river basin, and she also used scenarios for the future to understand what is going to happen to the ecosystem services according to different scenarios. We also did some economic valuations for Mozambique. So we provided the first ecosystem valuation assessment for Mozambique based on 5 or 6 ecosystem services. There are many other studies. I don't have time to go through all of them. So more recently, we've been measuring carbon sinks in China. We published this in a very important journal, which is Nature Communications. And we use a data set of individual trees for China, which includes 3 billion records, something like that, which is huge, to understand how different strategies of forest planning will have an impact on carbon sinks. Okay, so these are all important methodologies. They are all very different, but they always use geographical data. They also use machine learning. They also use process-based modeling. So we need to be aware of all those methodologies if you want to work on these areas. Okay, more recently also, we calculated the gross primary productivity for China over time. So this involved a huge quantity of data processing too. We're talking about China, is a very big country. And when we are working with satellite images with 30 meters resolution and things like that, the data becomes very, very heavy. But in the end, we created this data set and we published in this journal. And the data is also available for free for download. Okay. Also, an important project we developed at Nova AMS was the Eusébio project. So we did the first assessment of ecosystem services for Portugal. So we published a journal, in several journals, but we calculated ecosystems also based on current land cover for 6 ecosystem services. And we also calculated monetary evaluation. Okay. Yeah, so this is what we did. And also we measured, so the stakeholders is a very important component in ecosystem services. So we don't end up in our offices just creating maps that nobody will use. So if you really want this to impact society, we need to involve decision makers that use this kind of information to implement their policies. And this project was also done with this in mind. So we consulted stakeholders. We did a session at Nova AMS before COVID. We did a presential session with 30 stakeholders. And then we also did an exercise to see if their perception of ecosystem services, of the value of ecosystem services, was the same as if we measure them using data. Okay, so we did this comparison, and we found that there was a mismatch between the perception of ecosystem services by people and the values that the data gave us using models. So, and this mismatch was 30% higher than models, so which is huge. Okay, so either models underestimate reality or people overestimate it, or both, I don't know. So what to take from all of this? So technology is improving. So this is a very interesting area. We have more and more satellites. We are using more and more artificial intelligence for doing the calculations. This is incredible. I've been using Python. I've been using many different models, many different validation techniques. So we need to know how to work with these tools. The integration with ground data also is becoming more and more consistent. But we need to understand that the main challenge is not technology. Technology will always get better. It's always the interpretation, okay? Of course, AI is also playing big role here. Actually, we are finalizing a paper about AI for ecosystem services. It will be published soon, hopefully. I still don't have it here. So involving stakeholders is important because we want to impact society, because this is related to sustainability. We don't want this to live just for publishing papers, and we really want to involve decision makers on this so that the decisions become more informed and that they have a positive impact on nature, which is something we all care about. So, key takeaways. So let me just leave you with this. So, sorry about disappointing you. We are not using remote sensing to measure ecosystem services. We are measuring ecosystem service indicators. So these are approximations, and indicators are not services, okay? Of course, we are going to create very interesting maps in the end, always. But maps are not reality. We should always be very careful. What do they mean? If they are credible, so we should always try to use some kind of validation. Technology is improving, so we have higher resolution data, but higher resolution doesn't mean higher understanding. Sometimes it really means the opposite, because we are more confident and sometimes we are making bigger mistakes. So yeah, so that's what I had to tell you today. So thank you very much, and I'm happy to take any questions now. Thank you. Tá mute. You're muted.
Okay, sorry about this. Thank you very much, Pedro, for such a clear and enlightening lecture. Pedro is now happy to take questions from the audience. So please use the chat if you'd like to place a question. Okay? While you think about your questions, I'm going to start asking a few questions. So the first one is, I'm curious. So which ecosystem services are currently the most feasible, to monitor with certain degree of reliability using remote sensing? And which ones, in your opinion, present the greatest challenges?
Yeah, I think for answering that question, I would refer to the paper from Bruna, which I talked about, which is a literature review she made for how to use remote sensing to monitor ecosystem services. She does a very extensive job. But to answer very quickly to that question, I can tell you that the most common ones are those that exhibit a strong biophysical signal, like carbon productivity, water-related process. And the most difficult ones are like biodiversity, so we cannot measure that directly from ecosystem service indicators, or cultural services like parks, benefits that people, or the quality of the landscape, things like that, or the perceived quality of the landscape. So those are more difficult to measure because what we measure or we observe are functions, but not the service itself, right? So, yeah.
Okay, all right, thank you. I'd like to, stress that the audience can make questions, but I will go on. So one of the things you mentioned in one of your, in your talk was about machine learning and GeoAI. Do you think that it will significantly change the way ecosystem services are derived from Earth observation data, or they're just fast, they are smarter? What do you think the improvement will be?
Yeah, machine learning has a big impact on ecosystem services, as in everything we are doing now today. I think everyone working in the university is using AI one way or the other for different areas of knowledge, and the ecosystem services is not an exception. So we can improve prediction, we can improve data integration with AI, but it doesn't solve the core issue, which is interpretability. Okay, so we can use techniques like explainable artificial intelligence, which I'm using in some of my recent works, with SHAP values, but the ecological interpretation is still something that should be done by the human. And also, again, AI doesn't solve the integration also with the stakeholders, which is something that should always be part of the process if we want this to be used for sustainability objectives. Yeah.
Yeah. Okay. So you emphasized a lot this the importance of the stakeholders in this process. In your experience, how easily can remote sensing-based ecosystem services indicators be translated into tools that policymakers or land managers can actually use?
Yeah, this is also very interesting. So I mentioned two projects. One was about Bordeaux. We actually developed a project. We had stakeholders from different areas of society, from ONGs, from water management, from territorial management. And stakeholders have conflicting interests, so they always try to preserve what is more important for them, right? So one thing about ecosystem service is that we try to find a common ground for everybody. But I would say that we should provide data information that is linked to the decisions they need. They need robust interpretable metrics, but the challenge is always the translation and not computation. So this is as a human part that I think AI doesn't solve. So we need to work in groups of people, so we understand each other's needs, and AI can facilitate the process, of course, it does, but we need to involve them and we need to provide them information in a format they understand. They are not necessarily GIS experts or machine learning experts or invest experts. So we need to create the indicator that fits the purposes so they can actually adopt them and use them. Right.
Okay, all right, thank you. So we have a question comment now from our colleague Gudrun Valentin, whom you know very well. I'm going to read it out for you. Okay, so her comment is about the currency of ecosystem services. So she thinks that us as spatial scientists can offer space instead of dollars to give value to ecosystem services. The main difference is that space is finite, whereas money is not. For example, how much money is all the water in the world worth? In her perspective, there can't be a money tag to this. We need this water to live, so it's non-negotiable. So how would you comment this comment?
Hi Gudrun, nice to listen from you. I cannot see you, but so this is an interesting question. I think the monetary valuation is a very important aspect in ecosystem services because we want to involve decision makers, and if we add money to the equation, everybody, policymakers will understand much better the concept and will also be able to sell it more easily to everybody, right? But yeah, so the calculations that have been made with dollar values, they are all very, very subjective, I would say. Not all of them are easily demonstrable. There are many techniques in economics that can be used. I think in the PowerPoint I've left there a link for that. There are several methods. There are these species of scientists called ecological economists. They only work on these topics. and they come up always with sometimes very creative ways of assigning values or monetary values to those ecosystem services. And there are journals just dedicated to this kind of calculations. Some of them are more credible, some of them are not. But what is true is that some of them are really being used in reality, like carbon credits in the United States, or even in France, they already have laws, compensation laws for ecosystem service. So if you want to do some kind of intervention and you destroy some ecosystem services, you need to compensate monetarily the community with the values that were extracted from them to do that new project. Okay, so this is a serious issue. So, and we should be a little bit worried also, because when we start adding money values to everything, then we are also adding a way to create more taxes, right? And who likes taxes, or who likes to pay taxes, right? So that's how things are going. I'm not sure if I answered the question.
That's okay. All right, so we have another question from Thomas Strasser, and the question is, what are your thoughts on the assessment of uncertainty in satellite-based ecosystem service assessment using AI?
Yeah, that's a good one too. I've seen many works that use remote sensing derived data as input for machine learning models. And then we use usually those 80% training and testing using the same data instead of using external data sets. So we have these circularity problems that are very common in scientific papers because they are not actually validating with independent data the results they are obtaining. They are just using a subset of their data set to validate the results, which is not very strong. And sometimes, and I can see that most of the times we get results which are really fantastic, always 90% or more of accuracy. But the problem is not there, as I mentioned there before. The problem is on interpretation, okay? Sometimes even if we get very good results in those kind of validations, the interpretation is not really, the ecological meaning, what does it matter for decision making? That's what is really important, and that's why we should put more effort in the validation.
Okay, all right. So we have another question from Nuno David. It's also on the use of machine learning. And the question is, can you go beyond automatic classification tasks, okay, such as land use mapping, all right? So specifically, can machine learning be used to directly estimate the ecosystem services? And if that's the case, at which stages of the assessment workflow do you think it's going to add more value?
Yeah, I've been using, and not just me, hundreds of people that work on these issues. We have been using machine learning, not just for classifying land cover. For instance, in one of those papers I mentioned before, we estimated gross primary productivity, which is a near-infrared satellite product for China. And we created a machine learning model using different algorithms like XGBoost, random forest. And we use multiple variables like precipitation, temperature, forest fragmentation, and other variables to try to replicate the GPP, the gross primary productivity. So we can actually try to simulate products that exist and try to explain them then with explainable machine learning, for instance, explainable AI, which are the most important variables, how do variables relate with each other, and things like that. So we go a little bit beyond the black box nature of machine learning. right? So there are many papers with XAI, which you can read, and they also try to add some interpretability to the machine learning process. And then you can also use machine learning to estimate future scenarios. Okay, so machine learning can be used in several stages of the process.
Okay, so we have a final question because our time is finishing, from Thomas Strasser again, and the question is: what do you think? Which assessment framework, SciSys, MAIAs, etc., aligns best for the assessment with remote sensing-based methodologies?
Oh, that's a good question. I don't know how to answer. That's something I need to study. There are many classifications of ecosystem services, but actually I never thought about which one is better suited or most suited for remote sensing derived ecosystem service indicators. But I need to study that one. Thanks for raising my curiosity also.
All right. So I believe many of our people in the audience today are probably young researchers or students. So if you are advising these young researchers or students, that are entering the field today or recently, what skills or research directions should they focus on to make the biggest impact in ecosystem service monitoring? So what are the areas that you think could develop more?
Yeah, I think there is no such thing as a graduation in ecosystem services. There are master programs, or you can do a PhD on that, or if you are a curious person, you can study on your own. But I would say that as base, you should know about remote sensing. You don't need to be a big expert, but you need to know what is a satellite image. You need to know spatial temporal resolution, how to classify images, what are the derived products that we can use from remote sensing, etc. You need to know about GIS. Okay, you need to understand very well what is spatial data. Then, depending on the areas of application, maybe you need to understand ecology, maybe you need to understand biodiversity, maybe you need to understand economics. Okay, it can be a very multidimensional set of skills that you should have. Typically, we don't work on this alone. We have experts. I worked in places where they were ecological economists, and I was the guy with GIS and remote sensing. So it's usually a multifunctional team. But the challenge is not so much producing maps or knowing about machine learning. So you need to know about data science nowadays. That's, I would say, mandatory. You need to know about Python. AI helps you a lot. Sometimes I think with the ChatGPT and those tools, Grok or Claude or whatever, they can really help you processing data sets, but you need to know what you are doing. Otherwise, you'll end up with something that you cannot actually defend. But the challenge, and the real challenge, is not getting to produce those beautiful maps in the end. The challenge is to produce meaningful, defensible interpretations. Okay, otherwise nobody will use your analysis for anything, right?
Okay, all right. So thank you all for your participation and thoughtful contributions to today's seminar. I believe this session has offered valuable insights into how to monitor dynamics in ecosystem service indicators with remote sensing, and it has been a pleasure to continue our celebration of the 25 years of UNIGIS Portugal and our Master in Geographic Information Systems and Science. Our next seminar will take place on May 27 and will focus on marine data to enable digital twins of the ocean. Very interesting topic as well. So we look forward to seeing you there. Thank you, have a great evening, and thank you very much, Professor Pedro Cabral, again, for being with us today.